Hello, my name is Pierre Lemacares, and this presentation will be about setting up for high pressure data collection on the Chrysalis Synergy S using Chrysalis Pro, the Rigaku program for single crystal data collection and data processing. So in this presentation, we will see how to mount and center a high pressure cell on the Goniometer, how to center the crystal that is in it, and how to screen that crystal, and finally how to set it up for data collection within that high pressure cell. So let's first go through what is needed on the hardware side to proceed with a high pressure experiment. Here is a picture of the Chrysalis Synergy S, which I'm going to use for you today. So this is actually going to be a live demo, and you see I've got a video feed for you so that you can see what I do on the goniometer to whenever I'll be mounting the DAC and so on. So here is now a table summarizing the specifications of the Chrysalis Synergy S, and here is a picture of the diffractometer itself. The first thing I'm going to talk about is the source. The source is a microfocus seal tube, and you have the choice of copper radiation, molybdenum, or silver. Now you see that the molybdenum and silver options are highlighted. This is because these radiations are the radiations of choice for high pressure work. People basically never use copper for high pressure data collection because you would lose too much data there. And the reason for that stems from the fact that the crystal is really buried deep within the high pressure cell. So if you look at it in more details on the left-hand side, the crystal is really mounted in the middle of the gasket here, then bordered by two diamonds, which themselves are bordered by two backing discs. And then when you put all that together, you come up with that chamber. And in the core of it, the crystal resides. However, access of light to that chamber, or to the crystal inside that chamber, is pretty restricted. It's actually restricted by that conical aperture. So as a result, there are lots of reflections that will be lost, because only those reflections coming out of the high pressure cell via this conical aperture will reach the detector. So the idea here is therefore to squeeze as many reflections as possible within that aperture, and you do that by choosing shorter wavelengths. So, and this is well explained by the Bragg's law. Here, d being the d-spacing of a set of diffracting planes, and d is always constant. Your crystal doesn't change however you run your experiment. So according to the Bragg law, if you decrease the wavelength of the incident X-ray beam, you also have to decrease the theta here, which is the angle of diffraction, of reflection. So that's why when you go from copper, whose wavelength is at about 1.54 angstroms, to moly at about 0.71 angstrom, to silver at about 0.56 angstrom, then you keep decreasing the wavelength, and therefore you keep decreasing the angle of diffraction for the reflections generated by these various sources. So that's why molybdenum and silver are the wavelengths of choice, because with these two wavelengths, you really squeeze together the diffraction pattern through a smaller area. Copper, of course, will work also, but you will lose too many reflections. Mostly, you will never be able to go beyond a certain data resolution, because the reflections with a higher angle of diffraction will never be able to get out of the cell. So for those macrofocus seal tube sources, you have the choice of actually of choosing one or two sources. And here is one, here is the second one. People doing high pressure crystallography are more likely to go for the dual source option, whereby they would use molybdenum or silver, whichever one they have, for their high pressure work, and then the copper source for their work on crystals mounted on loops, at least for the organic crystals. Next, on to the beam. So the beam generated by the crystal check by the Chrysalis Synergy S is pretty small. The full width at half medium is 100 microns for molybdenum and 120 microns for silver. So the full width at half medium being the width of the beam at half its height. So if your beam has the proper Gaussian shape, you already have 50% of the the full beam intensity coming through that area of about 100 microns in diameter. And so that makes up for pretty small beams. And of course, the smaller the beam, the less beam clipping you have when the DAC rotates in the beam. And this is, again, due to that conical aperture. On the side of the beam, you have the same conical aperture as you have on the side of the diffracted reflections, so that when you rotate your DAC into the beam more and more, at some point the beam will start getting clipped by the edge of that conical aperture. And if you rotate even more, then the beam will miss the conical aperture altogether and be blocked by the body of the cell. Next is the goniometer. So we have a 4-axis kappa goniometer on the Chrysalis Synergy S. Here is the first axis phi, which is along the axis of the goniometer head, and here is kappa. Now here I want to draw your attention right away on the fact that kappa is tilted by about 45 degrees relative to the vertical axis, as well as relative to the horizontal direction here, which is the beam. So take note of that, because I will have to mention it later in this presentation. And then you have omega, which is always the vertical axis and the axis along which the data is being collected, and 2 theta, which allows the detector to swing on both sides of the beam so that you can collect both your low resolution reflections and your high resolution reflections. Last but not least, you must also use a high pressure kit to run high pressure data collection. And that kit consists of a shorter collimator and a longer beam stop. On the picture that is presently displayed, the beam stop and the collimators are configured for configured for crystals mounted on loops. You see that the collimators are pretty long. Their tips here get pretty close to the sample position, so that the X-rays coming out of the collimators has a shorter amount of air to go through before to reach the crystal. The same way, you want the crystal to be close to the sample position, so that you can bring the detector close to the sample position as well. So the detector that we use on the Chrysalis Synergy S is a hybrid photon counting detector, the HiPix 6000. And one of the many advantages of that detector is that you can bring it close to the sample position without having to worry about possible overlaps between neighboring reflections. So as a result, since you can bring the detector close to the sample position, you want a short collimator. However, what we have on our system here, you see that my collimators are shorter, leaving a wider space between their tip and the sample position. And the beam stop here is further away from the sample as well. So the beam stop has an additional elbow here that pushes the cup of the beam stop further away from sample position. And this is obviously to create more space at sample position, because your high pressure cells are pretty bulky. So now that we've seen what is needed on the hardware side, for the rest of this presentation, I will use a document that I wrote up and that lists all the steps that you have to go through to set up for high pressure data collection. So there will be 5 sections. First one being setting up for high pressure. Second one, defining the opening angle of the DAC in your data collection program, here Chrysalis Pro. Third section, we'll see how to mount and align a DAC on the goniometer head. Number 4, we'll see how to center the crystal. And number 5, and last one, we'll see how to screen the crystal and set up for data collection. So let's go back to the beginning here and start reading what this kind of tutorial tells us, really. So it tells us to open Chrysalis Pro by selecting high pressure mode. So let's do that. I will open Chrysalis Pro here. And you see that as soon as I open it, Chrysalis Pro asks me to choose a mode, either the standard mode, which would be for crystals mounted on loops, or high pressure mode, which is what we want here. So basically, I'm choosing a high pressure mode. It's click yes, and then let Chrysalis Pro run its system initialization. Well, this is already done, just took a couple of seconds. And now let me resize the window for Chrysalis Pro, as for the rest of this presentation, I will kind of juggle between different windows. So why do we have to set up Chrysalis Pro in high pressure mode? Well, this is really because, again, the high pressure cells are bulky, and so Chrysalis Pro need to use a more restrictive collision model when a high pressure mode is being used. Via that restrictive collision model, the motion of all axes will be much more restricted, especially the detector distance. Remember that I said that for when crystals are mounted on loops, we collect the we collect data with the detector at about 30 millimeters. However, we can't do that here because because of the presence of the high pressure beam stop, and therefore the minimum detector distance is set at 60 millimeters. So again, if I look at the system here, if my detector is currently at about 60 millimeters, close to the beam stop. If I had selected the regular mode or the standard mode, Chrysalis Pro would have keep driving the detector to its minimum distance for regular work at 30 millimeters, and obviously it would have hit the beam stop. So that's why you want to set up Chrysalis Pro in high pressure mode. But once you have done that, then you no longer have to worry about any possibility of collision. And I will prove it to you. I'm going to open the command line here and ask Chrysalis Pro to drive the detector to a distance shorter than 60 millimeters. Let's do it at, let's try 59 millimeters. So as soon as I push enter, you see that Chrysalis Pro outputs a collision error message. So you see, you don't have, at this point, you no longer have to worry about possible collisions between the different hardware of your diffractometer and the high pressure cell. So now there are a few more things to set up on the hardware. So they are listed here. First, you must ensure that you are using your moly source or silver if that's what you have. And if you are on copper, then please switch, right? You cannot use copper really. Then you have to raise the cryojet, which is what I've done here. Basically, I move the cryojet up within its conduit here, again, to leave more space at sample position. So if you are switching from working with crystals mounted on loops, you want to remove the standard beam stop and mount the high pressure beam stop. It's really easy to do that on the Synergy S. There's a thumb screw here, which you loosen up to remove the regular beam stop. You mount the high pressure beam stop and tighten it with that same thumb screw. So now every time you change the beam stop, this is good practice to verify that there is no direct beam leaks around the cup of the beam stop. And if there is, sometimes it will happen to you. Not to worry, it happens to everybody. But if there is, it's easy to manually push on that beam stop or pull on it until it's properly aligned with the beam. Now, once you have set up your beam stop, then you probably have a new shadow from that beam stop on your diffraction images. And again, this is good practice to verify in Chrysalis Pro what is the mask for that shadow in the program. So I will show you what I have here for my system. So it says here to open up the CCD pull-down menu, which is located at the bottom right of the Chrysalis Pro interface down here. Select Adjust Beam Stop, and then open up the Edit Beam Stop dialog. And then when I display the shadow that I have currently for the beam stop, so this is what I have here for my system. All right, so we've done, once you have prepared all that, then you're good to go, or you're good to keep going forward. And here we are reaching the second section where we're going to define the opening angle of the DAC in Chrysalis Pro. So why do we have to do that? Again, this is because the crystal is buried deep into the DAC. So just like we saw previously, then the diffracted reflections can only get out of the cell through a restricted conical aperture. So at non-zero phi and omega rotation angles, there will be shadows appearing on your diffraction images. And this is what I mean here. So look at this schematics, which represent a top-down view of the experiment. Imagine yourself standing above the goniometer, looking down at the high-pressure cell and at the crystal, the red rectangle here. So the source is at the bottom. Here is the incident X-ray beam, and the detector is at the top. In this particular orientation of the high-pressure cell, there are some reflections coming out of the crystal and coming out of the cell and reaching the detector, but they are only reaching the left-hand side of the detector, leaving the right-hand side basically completely blank. And that's because those reflections that would hit the right-hand side of the detector are basically missing the conical aperture here and never come out of the crystal chamber here. So as the high pressure cell is rotated clockwise, then more reflections are allowed to reach the right-hand side of the detector, making the shadow here on the detector basically a bit smaller. Rotate it a little bit more, and now you have the high pressure cell facing exactly the source on one side and the detector on the other side. And this is when you allow the maximum amount of reflections to come out of the coming out of the cell to reach the detector. So here, virtually, you're using almost the entire area of the detector, almost all of it. And as you keep rotating clockwise, now you're starting blocking reflections that would have hit the left-hand side of the detector. Now you're having a shadow here on the left-hand side of the detector, and that shadow grows on the left as you keep rotating clockwise. How does that translate onto your diffraction images? Well, here it is. If we go back to the original orientation of the DAC, again with reflections hitting the left-hand side of the detector, that's the kind of diffraction images that you would have here if you look at the right-hand side of this slide. And with almost the entire right half of the detector being shadowed from diffraction and being completely blank. And as the high pressure cell is rotated clockwise, then the diffraction travels from the left-hand side of the detector to the right-hand side. So if I play that for you again back and forth, looks like an eclipse almost. And there it is, okay? So that was for what happens on the side of the diffracted reflections. But the problem is the same on the other side for the beam to come in. Basically, the X-ray beam only has a restricted cone to go through as well to reach the crystal. So at higher phi and omega rotation angles, meaning if you rotate too much, at some point the X-ray beam will actually miss the DAC opening altogether and instead be blocked by the body of the DAC, and therefore no diffraction will occur in that instance. And this is what I mean here. If I rotate that high pressure cell further clockwise, then the beam is missing the conical opening altogether, and it never reaches the crystal. And as a result, I get a completely blank diffraction image. Now, obviously, the amount of rotation allowed along phi and omega is directly related to the size of that conical aperture, or also, and therefore it's basically directly related to what we call the opening angle of the DAC, so the opening angle of that cone here. And this is the opening angle that you must enter in Chrysalis Pro. And there are two main reasons for that. The first one pertains to the strategy. So the strategy algorithm first must avoid the orientations of the DAC that will block the X-ray beam and create blank images, of course. But number two, for those images that will have reflections on them, the strategy algorithm must also know which areas of the detector will be hidden by shadows. So it knows which reflections will be lost in those shadows. And this is only once it has all this information that Chrysalis Pro or the strategy algorithm can collect or optimize the strategy to collect as much data as possible. Mind you, though, even so, even with an optimized strategy, because there are still so many forbidden DAC orientations and so many reflections that will be lost, data completeness will always be lower or much lower than the data you would have collected on the same crystal mounted on a loop. The second reason is because pertains to data integration. So the data integration algorithm must also know when detector areas of the detector are being shadowed, so it doesn't use these shadowed areas into its background calculation and background subtraction. So how to enter the opening angle of the DAC in Chrysalis Pro? We actually enter the half opening angle. Okay, so we'll go back to Chrysalis Pro, go to Start Stop and other experiments as explained here. So let's do that. Start Stop, other experiments, and then high pressure experiments. And then here I enter the half opening angle of the DAC. See it as telling Chrysalis Pro that once the cell is properly aligned and therefore its face is properly perpendicular to the incoming beam, then you can rotate by 40 degrees counterclockwise and 40 degrees clockwise to collect data. Now, at first, all you can do is trust the opening angle given to you by the manufacturer of your high pressure cell. It doesn't mean that this is exactly the high pressure that your specific cell has. It could be a little bit larger or a little bit smaller. So the best you can do is collect a couple of data sets, and after you've done that, you will have a better idea as to what the actual opening angle of your specific high pressure cell is. All right, so now that we have done that, we can move to section number 3, and now we're actually going to mount and align a DAC or high pressure cell on the goniometer. So first, a reminder, bring phi to 0, and I've got phi at 0 here already. Move the detector away and put the cover on, because now I am going to be working in the goniometer area, and I don't want to hit the face of the detector. So to do that, I go back to the command shell here, use the GT command again, that stands for go to, D for distance, and I'm moving the detector far back to 150 millimeters. And you see here on that video feed how the detector moves back. Okay, so now I'm going to walk up to the machine, open the door, and start working live in front of you. So I can first remove what is mounted on the goniometer head at the moment. And then reading the tutorial again, we can now basically dismount the goniometer head and remove the flat magnet that is mounted currently in the goniometer head and mount instead the DAC or the high pressure cell. Okay, so let's do that. To do that, I use the tool that you also used for centering crystal, and then I remove the magnet here. Now, pick up my high pressure cell, and let me show it to you. This is the high pressure cell that I'm using today. Here is the first face of the cell. 180 degrees further, here is the second cell. Here is the pivot that I will use to that I will insert inside the goniometer head to mount the high pressure cell. Now it says here, make sure the face of the DAC would face the beam at phi 0. So if I look again at how my goniometer head is mounted or is oriented at phi 0, I keep that orientation, and then I mount the cell in that orientation and make sure that the face is facing that way, facing the beam, instead of the cell being rotated 90 degrees away, basically. Okay, and all I do here now is by eye, I will make sure that the axis of the cell, this axis here, and that axis there, are basically aligned with the two axes or with the axis of the goniometer head, which are basically the two knobs here and there that you usually use to center your crystal when the crystal is mounted on a loop. So just adjust or rotate the high pressure cell here this way, right? So as to have it more by eye aligned with the axis of the goniometer head. Once this is done, picking up the tool again, you can tighten the cell inside the goniometer head. There. So this is done, and I can mount the goniometer head again back onto the goniometer with the high pressure cell on it. And there it is. There we have it. So now we will now fine-tune the orientation of the cell inside the goniometer head, because we've only done it by eye at the moment, but we need to fine-tune that so that again the axes of the cell are better aligned with the axis of the goniometer head. Sorry. So why do we use actually the axis of the goniometer head for that? This is because we know that at phi 0, one of these axes will face the beam here, and the other one will be perpendicular. So if we align the axis of the cell with the axis of the goniometer head, we'll know that the face of the cell faces the beam. All right, so now let's go on and further or approve the alignment of our cell in the goniometer head. So it says here, so that this is still basically a coarse alignment, right? So bear with me here. To do that, we need to bring the high pressure cell in its horizontal position with the faces pointing up or sideways. So that means that that cell that is currently vertical will have to bring it in its horizontal position with the faces here pointing sideways or up. Okay? So, however, this is something that is hard to figure out in the kappa geometry. And here I'm getting back to one thing I said at the beginning of this presentation, where I said that the kappa axis is basically tilted here. Here is my Sharpie pen indicating the kappa axis, and I said that the kappa axis is tilted relative to the beam by about 45 degrees. And because of that tilt, it's hard to figure out by how much to rotate along kappa to bring the cell in its horizontal position with the faces facing either sideways or upwards. Instead, we will use a chi geometry to do that. Okay, and here is what a chi goniometer is, or what the chi geometry means. So let me go back to my presentation. That picture here on the left-hand side represents a chi goniometer, also called Eulerian goniometer. So a chi goniometer is made of a full circle whose center is basically the position of the beam. Then the goniometer head can rotate the full 360 degrees along that circle around the beam, or around an axis, an imaginary axis that would be basically the X-ray beam. And that axis here is called chi. So chi basically is the axis that is along the beam. So now if you have a high pressure cell mounted on your goniometer head, to move that high pressure cell from its chi zero vertical position to its horizontal position, all you have to do is rotate by 90 degrees. So that's why we use a chi, or the chi geometry. It's because this is easy to figure out that you only have to rotate by 90 degrees. Now those chi goniometers do exist. Here is the picture for one of them, and Rigaku had their own chi goniometers before. We didn't actually have the full circle. We had a quarter circle. But once again, this is no longer what we have here. What we have is a kappa geometry goniometer, whereby the kappa axis is tilted relative to the beam by about 45 degrees. So what we have to figure out is how to translate that 90 degrees angle along in chi to the kappa geometry. Fortunately, we can use Chrysalis Pro to do that. So if I go back to Chrysalis Pro now and to the tutorial, the tutorial here says to use the command GTE. So let's go for it. GT, remember it stands for go to, and then I choose the option E standing for Euler. Then when I push OK, an additional dialog opens up, and you see that basically Chrysalis Pro is telling me that it expects angle values in Euler geometry, and it will take care of translating those Euler angles into kappa angles. So because we have 4-axis goniometer, I need to enter 4 angle values in this very order: omega, theta, chi, and phi. So here is a set of angles that I like. So 19 first for omega. It doesn't have to be exactly 19, but this is something suitable for me here today, so that you can, using on the video feed that I have set up for you, you can keep seeing what I do on the goniometer. Then omega theta minus 50. Again, it doesn't have to be especially 50 degrees. This is just to push aside the detector a little bit. But now the last 2 angles, chi and phi, must be specific values. So chi, we said, must be 90 degrees. And then phi can be 0 or 90, as indicated here, according to the tool that you use for the next step. Let me use 0 for now. And see that as soon as I entered all 4 angles, Chrysalis Pro translated them into kappa geometry right away. So it's ready to go. All I have to do is push the button GTA, and here is the full command line that will be used now by Chrysalis Pro to move the cell. Push enter, and now you will see how the goniometer moves to its horizontal position. And brings and orient the cell so that its faces basically sit sideways at the moment. So now we have, again, we will adjust the rotation of the cell inside the goniometer head. And there are two ways to do that. The first way to do that is to use a triangle square like this one. Now you see the edge of the platform of the goniometer here. So that platform should be perfectly horizontal if your system has been properly installed. So now what you have to do is to put one edge of the triangle square on that platform, on the goniometer platform, and then slide it towards the face of the high pressure cell until the other edge of the triangle square comes flush with the face of the cell. And once you're there, basically manually you rotate the cell so as to bring the face of the cell perfectly parallel, or as perfectly as possible, the face parallel to the edge of the triangle square. So that's one way of doing it. The second way of doing it is to use a bubble level. Now it's usually hard to settle the bubble level here on the side of the high pressure cell. Instead, this is when you need this, one of the faces to face up, so that you have a larger platform to put or to settle your level. And to do that, this is where use the second set of angle values displayed here. So let me put them in. GTE again, 19 minus 50, 90. So that hasn't changed from before. But instead of entering a value of 0 for phi, now I enter 90. And so you see that as I do that, this is when the goniometer rotates by 90 degrees along phi, bringing the one face of the cell up. And now I can settle my bubble level here, and basically check the bubble to adjust the position of the cell. And again, I can manually rotate the cell one way or the other, and you see that how when I do that, how the bubble actually moves. Okay. Yeah. So if you use a bubble level, it is good practice also to turn the level 90 degrees and orient it this way, so that now you verify also in this direction whether your cell is horizontal or whether it's tilted upwards, for instance. Maybe the pivot that inserts into the goniometer head is a bit bent, or tilted downwards. So if it tilts downwards, it might be because the cell is sagging under its own weight, which would be a sign that you may not have tightened the cell inside the goniometer head well enough. So here everything seems okay. Let me verify again in this direction. No, here it's good. So once you're happy with what you've done, it's good to give it another squeeze here to make sure that the cell is tight within the goniometer head. All right, so now we have our cell aligned, pretty much aligned with the axis of the goniometer head. Next thing that we have to do before to collect data is to now center the crystal. Now, centering the crystal starts the same way as when you have a crystal mounted on a loop. So let's go for it. Basically, in Chrysalis Pro, you open the crystal centering window by pressing or striking the key F12 on your keyboard. So Chrysalis Pro basically starts at with the goniometer at its 0 position, kappa all the way down to 0. And all I have to do here now is push that button here, page down, to actually bring the goniometer into its crystal centering position. So it's not exactly the same position as I had before. This is now basically the cell is rotated a little bit clockwise, and this is because the crystal camera that I'm going to use now to center the crystal is here, and that camera is tilted a little bit to the right. Okay? So let's look for the opening of the DAC and the crystal. So it was just a little bit too low, so I'm bringing the opening of the DAC now with the crystal in it higher. All right, and then you can certainly adjust the horizontal position of the crystal as well. All right, so far, nothing different with when you have crystals mounted on loops. Typically now though, so if you have a loop, you would rotate by 90 degrees. But you see here on the video feed that once the cell is rotated by 90 degrees, now this is the side of the cell that is facing the camera, and therefore we can't see anything anymore of the crystal. So we can do nothing else but come back to phi 0 with the face facing the cell, and use basically that sledge, that knob here on the goniometer head to move the crystal up or down along the direction that is parallel with the lens of the camera until we bring the crystal here in focus. So let me try to rotate clockwise, for instance, and I'm going the right way here. And I adjust the focus basically as well as I can with the basically with that crystal centering tool. Now, is that the correct sample position? By just looking at the focus, did I manage to bring the crystal in its sample or add to the sample position? Probably not. I'm probably close, but the focus is really not good enough to bring the crystal really at sample position. And you can verify that by rotating by 180 degrees. It is likely that the focus now will be a little bit off, more or less off. And as it is here. So that means that the crystal is still wobbling around its proper sample position. Now, there may be another reason as to why we are out of focus here, and this might be also due to the centering or the alignment of the diamond anvils inside the cell. So let me go back to my presentation here, and here is what I mean. So in a perfect world, the diamond anvils would be perfectly aligned relative to each other, as well as relative to the axis of the cell. So that whether at phi 0 you look at the crystal through that diamond, or when you rotate to phi 180 degrees, you look at the crystal through that other diamond that will indeed get here once you rotate by 180 degrees, because those two diamonds are aligned exactly the same way, whether you look at the crystal through one or the other at phi 0 or phi 180 degrees, doesn't make any difference. You will see the crystal here in the camera the same way. So a good focus at phi 0 will be a good focus at 180. However, in real life, your crystals are, your diamond anvils are more likely to be aligned as such. And you see here that those two diamonds are no longer aligned with the axis of the cell, but they are no longer aligned with each other either. So now at phi 0, when you look at the crystal through that diamond, the light will be deviated a certain way. So you will adjust your focus here accordingly. But then when you rotate by 180 degrees again, now this diamond will rotate and come here, and you will look at the crystal now through that diamond. But now the light will be deviated a different way than it was previously, because that second diamond is not aligned in the same way as the first diamond was. And that will create a parallax error, which may contribute to the fact now that we see our crystal out of focus, so much out of focus at phi 180 versus phi 0. So the way we will correct for that now is, again, basically we have the crystal wobbling around its position, right? We have two different crystal positions at phi 0 and at phi 180 that yield a good focus. So that means that our crystal, as we rotate to phi 0, then from phi 180, back to phi 0, back to phi 180, the crystal is basically wobbling around the sample position and getting closer and further and closer and further to the camera. So we basically have to find the middle position between these two extreme positions. So the first thing we'll do is now to adjust the focus of that of the crystal again at phi 80 and figure out how much we have to sorry, we will do that again by using this tool and the sledge here on the goniometer head. So what we will do here is that we will adjust the focus of the crystal again, but now we need to count how many turns we have to turn here with the tool here to get the crystal in focus in that position. So the thing is that those tools don't have any mark on them, so usually I take a Sharpie pen and I make a mark on the tool myself. All right, so let's start rotating. So I'm going to rotate clockwise. And I seem to be going in the right direction. So this is one turn, one full turn already. This is a second full turn and maybe a little bit more. Another half a turn, and now I've got the crystal pretty much in focus again. So I just rotated that sledge of the goniometer head by 2.5 turns. Now again, I need to find the middle position of that. So that means now that I have to turn that same sledge here in the opposite direction by half that amount, which means that I will have to rotate clockwise now that sledge by a turn and a quarter. So let's go for it. So that was already half a turn, a quarter of a turn, sorry. And then another turn. So that should be the sample position or close to it now, because this is the middle position between those two extreme positions we had previously at phi 0 and phi 180. So now we're going to bring the crystal into focus again, but this time we're going to adjust the focus with the camera, with the crystal camera. So that knob here, the focus knob, doesn't have any mark on it either. So again, don't hesitate to use a Sharpie pen and make a mark on that knob. All right, so basically I'm gonna reach out here and turn that knob. Let's try to rotate it clockwise first, and I'm going the wrong way. So now I have to come back where I was before, okay? And I have to keep rotating now in the correct direction. And by what amount? Again, by 1 turn and a quarter. The same amount that I moved that sledge to reach the middle position of the crystal, then I have to rotate by the same amount with the focus knob of the camera. So counterclockwise, and I'm going here. Here is 1 turn already, and maybe another quarter. There. And then you see that just with a quarter, a full turn and a quarter, I brought the crystal back into focus. So now again, this is the crystal that is at sample position or really close, that is in focus. If I did a good enough job, if I rotate back to phi 0, I should have a similar focus. It's probably not going to be exactly the same, but hopefully this is similar. And indeed, it's pretty good. If you still see an out of focus crystal here, that means that you have to repeat what I just did. And it's not uncommon to have to do that 2 or 3 times to get a good focus at phi 0 and phi 8. Now, the last thing we're going to do before to collect data is the fine tuning of the horizontal position of the crystal. So now if I adjust the horizontal position of the crystal here, so I need to bring it a little bit to the right. There it is. And I rotate now to 180 degrees. And you see that the crystal, the center of the crystal no longer matches the crosshair, which is supposed to, which shows the center of the beam. And this is most likely because the orientation of the DAC here of the cell inside the goniometer head now has to be fine-tuned, but to the scale of just a few microns. And that few micron scale, there's no way that we could attain that kind of precision with just the triangle square or the bubble level. But we'll do that. We'll get that kind of precision now by using the position of the crystal itself. So the center of the crystal now is here. So the distance between the crosshair and where the arrow stands here is probably about 30 microns. And I know that by counting the number of little red tick that I have on the horizontal axis between the crosshair and the current position of the arrow. So one little tick represents 10 microns, and I have about 3 of them, so 30 microns. So you see, I'm not too far off anyway. So to correct for these 30 microns offset, I will do it again in 2 steps. 1/2 of that offset will be corrected with the crystal by using the sledge and the goniometer head, and the other half will be adjusted with the alignment of the DAC. So for that other half, I will literally rotate the DAC inside the goniometer head so as to correct for half of that offset. So half. So let's go and do the first half. I'm moving the crystal now to the left by probably a bit more than 1 graduation. There it is. And then to further bring the crystal, the center of the crystal to the crosshair, I'm just now going to slowly rotate the DAC in the correct direction. All right, so now it doesn't look too bad here. So if I did a good enough job, if I rotate back to 5-0, the crystal should be pretty centered also. If not, then repeat. I'll have to repeat what I just did. But it's not too bad. Now, one other thing I want to realize is that here the crystal is a little bit higher than the horizontal axis, but at 180, it is actually pretty well centered with the crosshair. So you see, it's not too high here. So at 5-0 and 5-180, the center or the position of the crystal is not exactly the same, although the height of the crystal is not exactly the same. That can only be due to a slight misalignment of the crystal, but there's not much difference here. So I would leave it as such. If there was more difference, you want to choose a height for the crystal that remains the same at 5-0 and 5-8. All right, so now we have a crystal center in the beam. I can bring the whole goniometer back to 0, back to its home position, and I'm getting ready to collect data. Okay. So remove the face of the detector, because since I'm about to collect data, close the door of the system, and I can get out of that crystal centering interface, and then reach the last section of this tutorial now that pertains to crystal screening and data collection. So remove the detector cover. I did it. It's a good practice to verify again your half opening angle of the DAC. Did you enter it properly? Did you remember to enter it actually? So I go back to start stop, other experiment, high pressure experiment, and indeed I have it at 40 here, so it's all good. So now I'm going to jump right away to the pre-experiment. Those of you who use Chrysalis Pro already know that you should really screen and then run up to a pre-experiment. The thing is that it's most likely you will have already screened your crystal in ambient conditions before to actually mount it inside the cell. After all, you want to make sure that your crystal is good before to go through the troubles of mounting it inside a high pressure cell. So as a result, at this point, you know what to expect from your crystal. You know it's a good crystal, and you know also what kind of exposure time to use for it. Okay, so I can go to edit the edit dialog for the pre-experiment right away. You can choose your data directory from this button here, and then implement a target I of a sigma and a target resolution for your crystal. Again, at this point, you know what to expect. So here I have a target I of a sigma of 15 up to a resolution of 0.8 angstrom. Okay, so to run the pre-experiment, I will also change that exposure time to 1 second, because I know by now that 1 second is plenty for my crystal. So I click OK, and now I can push start the pre-experiment. And as this takes place, we'll keep watching the what happens on the goniometer. So the shutter is now open, and reflections appear on the images, and you see that the cell is slowly rotating along phi. As images are coming in, Chrysalis Pro is already running an automatic concurrent indexing. So the first scan is almost over. It collects 40 images per scan. And now you see that the goniometer rotates the cell by 180 degrees to collect another 40 images, but from the other side of the cell. And again, as images keep coming in, Chrysalis Pro updates its indexing statistics here. So here are the unit cell parameters, the lattice, as well as the statistics here on the reflections indexed. At the end of the pre-experiment, the strategy interface opens up automatically. And at this point, you can certainly go to the lattice wizard and redo indexing manually by going to peak hunting and unit cell finding. And you can certainly look at your diffraction pattern in the reciprocal space as well. And this is what we got so far along A star, B star, and C star. So at the moment, Chrysalis Pro wants to collect 902 images in 17 different runs or 17 different scans, which will amount to 44 minutes of data collection. If you look at the plot down here, you see that mostly the second half of the data collection, the completeness does not increase much. Basically, Chrysalis Pro here reaches a plateau and it doesn't go beyond 37% completeness. At this point, all you do is add to the redundancy, but you don't gain in terms of completeness. And you see, that's what I said a little bit earlier, is that many of your data set collected in a high pressure cell will be of lower and maybe even much lower completeness. And here, this is not surprising that we get such a low completeness because the symmetry of our lattice is low, primitive monoclinic. So you may be okay with that, but if you want to gain time and you don't care about adding to the redundancy, what you can do is ask Chrysalis Pro to calculate a new strategy with a new target completeness. So if I put 37 here, 37%, and calculate a new strategy, so now I've got a lower redundancy, and Chrysalis Pro is asking to, or is setting up to collecting fewer images in fewer scans, and now we have a shorter data collection. If I switch this view to the table view, I see that the completeness here would be 37%, basically exactly. If you want to gain some more time, you can certainly decrease it a little bit, let's say 36.5%, and calculate a new strategy to again decrease the data collection time. And now I've got basically 29 minutes only. Okay? So that's only if you want to gain time, plus minus 1 or 2% completeness. If it doesn't, if it's not that important to you, then do like I just did. So Chrysalis Pro, by the way, knows about how long the data collection will take because it has estimated the exposure time. Okay, and it could estimate the exposure time because in addition to doing a concurrent indexing during the pre-experiment, it has also calculated the I of a sigma for the reflections coming out of those pre-experiment diffraction images. So knowing the I of a sigma I got with a 1 second exposure for the pre-experiment, now it's telling me that to reach a target I of a sigma of 15, like I set it up to, it needs to apply an exposure time of 3.42 seconds. Okay, so at this point, you're ready to start the experiment. You can name your data folder here as you wish, and then enter the chemical content so that the structure solution program that will run during data collection is better able to solve the structure. My crystal here contains tungsten and iodine. So I will just start the data collection and then stop this presentation, but I want you to see what happens at the beginning of the data collection. So what Chrysalis Pro always does is that it brings the goniometer back into its crystal centering position so as to take pictures of the crystal by rotating it by around or through 360 degrees along phi. And these crystal pictures are used afterwards for face indexing. Now, of course, many of these pictures are blank because oftentimes this is the side of the cell that is facing the camera, but you will still have some pictures like these ones here that will be useful to you to actually do some face indexing. Okay? So let it run and don't interrupt this process. You do need to do face indexing, and you will have some images here useful to you that should be enough. And then we'll let the first couple of, or the first few diffraction images appear, and then I will stop this presentation here. So again, now the goniometer gets into position to collect its first diffraction images. And there it is. So at first we get some beam clipping here, but we also start getting here some reflections. You see those reflections. So, and now we get a strong reflection here from the diamond, and otherwise this background here is the beam slightly clipping onto probably the edge of the conical aperture or the edge of the gasket. Okay, but that if we kept going, that would disappear at some point as the DAC here keeps rotating. And I'm going to stop here, and I thank you for your attention.